In this lecture, we're going to develop capability to simulate our vehicle forward in time using those dynamic equations we had developed previously. So we worked hard last time to develop our equations of motion, and we came up with all these time derivatives, right? And if we go and look at the code, we see that this derivatives function actually implements all of those 12 derivatives we were just looking at, but we call it 4 different times. And then we combine those to get our actual state update. So we're going to figure out what in the world we're doing here with with calling our dynamics 4 different times in a row. Okay, so let's go ahead and get started. So looking at these equations of motion, previously we had introduced this idea that we have a state x. So our state x is equal to, and it's going to be Pn, and we have 13 of these states all the way down to R. And then our dynamics, well, our state update equations are some function f of x u, which is equal to basically this set of functions. Right? So we have 13 equations, and these equations are a function of the state, right? So what we just denoted, as well as our input u, which for this chapter, we've said this is our f in our body frame and our moments in the body frame. So these guys are together form our input u. So we can see over here on the right side that we do have this function that is, and we could definitely see dependence on both our states and those forces and moments. Okay, so how do we use that to simulate forward in time? So we're going to come up with we're going to talk about a few different techniques, and they're all Runge-Kutta techniques. But the idea here is that we have our state update equation, and this, again, we'll call this x dot, right, is equal to dx dt. So we have our dynamics, and the other thing that we didn't mention previously is that we have an initial state that's known. So this is an initial boundary value problem. So we know something at the beginning, and the question is, what is x at some point in time where t is greater than t naught? We want to be able to know what our state is in the future, or simulate things going forward in time. So we do end up having x of t appear on both sides of the integral, or on both sides of the equation. So it's something that we need to solve and approximate. What we're going to do is we're going to split up this integral. This integral, we'll split it up into 2 different components, one from t naught to t minus ts, and 2 from t minus ts to the time that we care about. Okay, one thing to note here, so again, this equation that I'm pointing at, it's the exact same equation as above. We've just split that integral up. Okay, the bottom equation looks fairly simple. So if I circle in red x of ts, and that's really just applying this equation right here with t is equal to, instead of t, we'll define it as t minus ts. So this component is just saying, hey, those first 2 elements of the equation really just form x of t minus ts. Okay. So then we have one final portion to integrate. And if we assume that ts is small, where again ts is either we can call it our time step or our sampling period. If we assume that that's small, then we can use some nice approximation techniques for that. Okay, a key principle that we're going to use is that we can approximate this integral. And the first approximation we're going to do is RK1, or otherwise known as Euler's method, is we're just going to approximate it with a line. So in other words, we're going to evaluate f at an initial time, and we'll say that that gives us a slope for a line. Maybe I should pull up a line. Gives us a slope for a line, and we'll just say that this end state is approximately equal to x at time b. Okay, so it's just a first order approximation, but if our time step is really small, that's pretty good. We're just saying there's really nothing's really happening to our curve in between time A and time B, that it can be approximated good enough by a line. We can see in this little illustration that that's not necessarily true, and it never really won't be unless our state is evolving along a line, right? So as we come here, we can use this first order approximation using Euler's method, and what we notice here is this is just a time interval, and this is the dynamics, or our state update equation at the start of the interval. Okay, so that's fantastic. These are things that we know about, right? So we know what our state is at the beginning, and we can know what our limits of integration are. So if we look at our setup, so A is just t minus ts, B is equal to t. So if we look at the difference, B minus A is just going to be equal to t minus ts, which equals ts. So that's where we get this first component of. And then we're evaluating it at our initial time. So this is our initial time A. And we're going to evaluate using both our state and our input. So we can then approximate this integral as the length of our time step times the slope of our dynamics at that point, right? So we're just using this tangent approximation. So the numerical integration, we can write it as a routine where we start with x naught. At each time step, we're going to update with the previous state plus our sampling period times this function big x1. So let's see what this looks like. So if we start off at x naught, this is given. We're going to write that x1 is equal to, if we look at this bottom equation, it just tells us what we're going to be writing, right? So we have x naught plus we have our x1, or ts, sorry, ts times x1, which would be f of, and we say that's going to be x naught for this case, x naught u naught. x2 then is equal to x1 plus ts f of x1 u1. And we just keep going. x3 is equal to x at time 2, or step 2 plus ts f of x2 u2. All the way down till we get x of k is equal to, right, our equation that we have right there. So we've in effect discretized our system using an approximation for that integral between time steps as just our time period times our dynamics at that point in time. So the easiest approximation to do. Note that this is discrete. If we want to represent it in a continuous fashion, this one, we know that x of time t naught, well, that's given as x naught, right? Going forward in time, x at time t naught plus ts, that's approximated here as x1. X at time t naught plus 2 ts, right, is approximated as x2, and so on and so forth. And so x at time t naught plus k ts is approximately equal to this guy right there. So we have our discrete representation, but it represents our state at discrete points in time, and those points in time are given and established. Okay, so this is a first order Runge-Kutta method, and we could write it as RK1, or you'll also hear as Euler's method. Maybe I should write method. Well, we can do better than just approximating it at one side of the interval. So again, we're just trying to find that area under the curve. Well, if we knew how to evaluate our dynamics at a second point in time, we could use what's called the trapezoidal rule, and we'll just take the average of basically going forward with an integral going backwards. So we'll take the average of those two and say the average of the areas under those curves is going to be a better approximation than just evaluating it at the start time. Now, there's an issue with that, is that we don't know what it is at the final time, so we'll have to approximate it. So we use a first order approximation to get there. I'm getting ahead of myself a little bit. So again, we can use the trapezoidal rule for integration. It's just a way to approximate the integral or the area under the curve, right? Again, we have our time step, right? This guy is just going to evaluate down to TS. And we have something right here. This is just giving us our average, right? Because we have the two values in the average. And so that's where this guy comes from, is we have TS divided by 2. And then we're going to evaluate our dynamics at point. This is at our initial time, t minus TS, and our final time at t. Okay, so that's where we get this equation right here. So this is just TS over 2, and this component is just f of A, and this component is f of B. Well, the problem is, if we knew x at time t, we wouldn't do this. That's what we're trying to solve for, right? So we wouldn't, if x of t is known, then we don't need to even do any of this. But x of t is unknown. Well, we could approximate using our first order approximation was great, or was a way to find out what x of t was, right? So we could say that, well, x of t, for this evaluation, it's approximately equal to x at time t minus ts plus our time interval, times f of x evaluated at t minus ts. Oof, I'm running out of room. U at t minus ts. Okay, remember this is just our first order. Well, I'll just write it as, this guy was just our RK1. So we use our RK1 to figure out what x of t is. So we're approximating x of t. And then we throw it in as to use that as our approximation. So if you look here, down at the next equation, we can straightway take this guy, right? It's still f of A. And this guy right here is an approximation. This is almost equal to f of B, right? Where we've just thrown x of t in for our x variable. So this whole element that I'm going to highlight, this is just an approximation for x of t. And note, another thing that we note is that this guy right here, we just keep our input constant. So we could also have an approximation for what our, if we knew what our input was going to be, we could use that instead. But typically when we're solving this forward in time, we've calculated an input and we want to see how does that affect our state. So we haven't calculated our input. We won't calculate our next input until we know what the state is, and we use this feedback control law, right? So we just assume that we're keeping the input constant. Okay, so we can write this again using this, using a simple routine. And now we have two steps, right? Or maybe I should write not two steps, but two evaluations of f of x u, which is getting closer to what we saw in the beginning with the code, where we had 4 evaluations. So we start off, we know what our value is at time t naught, and then to get to the next step, at x sub k is going to be equal to x at our previous time, plus we have this average times our sampling period. And then we're just going to take the average. Remember, this is basically f of a, and this is f of b. So coming full circle, we have this f of a plus f of b over 2 times the interval. Okay, so to write that down, be more explicit, right, we would say that, well, x naught is given. x1 is equal to x naught plus ts over 2 times, and I'm going to just cheat a little bit and put a k minus 1 here. So we'll do our x1, k minus 1, and x2, oh, shouldn't be a comma there, plus x2, k minus 1. And in this case, we know what k is, right? It'll just be 1. 1, 1, 2, 1. And then again, we'll just keep updating our state. So we'll have x2 is equal to x1 plus ts over 2, and we're going to evaluate x, that should have been a 0. x1, 0 plus x, I'm really butchering that. x1, 1 plus x2, 1. All right, x3, let's see if I can get it right on the third time's the charm, right? So x2 plus ts over 2. We have x1, 2. Almost got it right. 1, 2 plus x2, 2. Right, and we keep going down until we have x of k is equal to, and then we have this exact equation. Okay, so this is a second order, and again, it approximates it as a trapezoid, right? So and just as a review, we're using an approximation within our approximation, right? So it's getting us less error, but there's still going to be some error there. Now we'll step through and we'll do RK4. RK4 now uses Simpson's rule for integration, and we're going to approximate the evolution of our state using a parabola instead of, in the RK2 we did a trapezoid, in RK1 we just used a straight line. So again, we can follow very similar formulations, right? We have f of a, and then we would evaluate of f of a plus b over 2. So this is the midpoint, and this is the end point. Okay. Well, we don't have the midpoint or the endpoint, so we have to approximate both the midpoint and the endpoint. And so what we're going to do is we're going to break this guy up into two components. Right? Seems kind of strange, and it would be strange if we left it as such. X1 is f of a. That's what we have been doing this whole time. X2, we're going to go. Notice this is halfway times our plus our state. So what we're doing is we're trying to get halfway over. So this is an approximation for our halfway point. And then we're going to do, again, we'll do f of a plus, and now we're going to go another halfway. We're using our approximation for our state from x2, this big x2, and then we go the full way to get our approximation for the final point. So we use these two approximations for our halfway, and then we use a third approximation for our full way of getting across. So just writing it all out, we have our x naught is given to us, and then our x1 is defined the same as before. x2, now notice that it is the halfway, so it's not the exact same x2 that we had for the trapezoidal rule, right? Because we've now divided it by 2 to get a halfway approximation. And then we get our second approximation for the halfway point in x3. And this big x4, now we do our full approximation, and this is now using the Simpson's rule. Okay, so we have our state is at discrete time step k is equal to, or discrete at k minus 1 plus, then we have the Simpson's rule to give us that state update. And if we go and look over to the code, so we can see how it's implemented, we have our derivatives. That's that f function, right, where it's a function of our state and our forces and moments. Okay, and then we're evaluating it just like we did previously, where we're going a halfway approximation, another halfway approximation, and then our full approximation. And then this plus equals is just going to be the state at the previous time plus, and then we have our time step over 6. So we're using Simpson's rule right there on line 220. Okay. So going back to this chart, this is just a visualization of the different steps that make up this RK4. So we're doing, yeah, I think that's pretty good. So we can evaluate our state. Sorry, I thought this was a slightly different figure. So yeah, so we're just taking the various components of our RK4. This is just showing where we're evaluating our integrals, or yeah, our dynamics. So x1 is evaluating it here at the beginning time. x2 and x3 are at the halfway point, and this big x4 is at the final point. We combine them together, and hopefully we're approximating our system as a parabolic function between those two time steps. So now we're able to simulate our state forward in time. This RK4 has a much lower level of error than the RK1. So this is typically your go-to. If you're going to numerically integrate something, use an RK4 as your first approximation, or a numerical integration library.